What are integrated rate equations? They relate concentrations of reactants or products to time. An IRE can be used to determine the amount of reactants or products after a period of time, or to estimate the time for a reaction to proceed to a certain extent. There are three equations. The zero-order equation A0 minus A is equal to KT, first-order equation ln A0 over A is equal to KT, second-order equation 1 over A minus 1 over A0 is equal to KT. Firstly, we have the zero-order equation A0 minus A is equal to KT, where A0 is the initial concentration, A is the concentration after a period of time, K is the specific rate constant, and T is time. In this structure, K is a constant that has a unit of m raised to 1 times time raised to negative 1. In this case of zero order, rate is independent of concentrations. For example, whether or not A changes its concentration, rate remains the same. In this example, we can see that A is doubled, but that did not affect the rate. Secondly, we have the first order equation ln A0 over A is equal to KT, wherein K and T are rate constant and time respectively. The value of K here has the unit time raised to negative 1. First order reactions have the structure rate is equal to Ka or rate is equal to Kb. First order reactions has a rate directly proportional to the concentration of one reactant. When given first order, the concentration of reactants proportionally affect rate. Below, we have the same example. But when the concentration of A is changed, the rate is also proportionally changed. The rate doubled when A is doubled. Last but not the least is the equation for second order reactions. We have the equation 1 over A minus 1 over A0 is equal to KT. The unit for K here is m raised to negative 1 times time raised to negative 1. Second order equations have the structure below. Ka squared or Kb squared or Kap. The two reactants have first order each, creating an overall of second order. The rate of second order reactions are proportional to the squared of concentration. In second order reactions, when a reactant is doubled, the rate is quadrupled. To determine the order of the reaction, we have the following hints. The problem may explicitly state the order. For example, compounds A and B react to form C and D in a reaction that was found to be second order in A and second order overall. As you can see, second order overall was mentioned, so the learner can directly proceed to the second order equation. In some cases, the equation or expression may be given, but in most cases, K may be given. Recall that when we have a zero order overall, K has a unit of m raised to negative 1 times time raised to negative 1. Then when a first order reaction comes, K has a unit of time raised to negative 1. Then for a second order reaction, K has a unit of m raised to negative 1 times time raised to negative 1. Do you notice the relationship of K and the order of reaction? Time raised to negative 1 remains constant in all equations, but it is the unit of molarity that changes. For succeeding orders of reaction, since third and fourth orders are still possible but quite rare, the following structure can be followed. M raised to 1 minus order times time raised to negative 1, giving the K of a third order to have the unit m raised to negative 2 times time raised to negative 1, and the K of a fourth order to have the unit of m raised to negative 3 times time raised to negative 1.
Before we forget, we'd like to show you that these integrated rate equations can be plotted in a y equals mx plus b format to give a linear plot. Y is the variable plotted along the vertical axis, while x is for the horizontal axis. M is the slope of the line, and b is the y-intercept. Let us arrange the zero-order rate equation. Concentration A0 minus concentration A is equal to KT, where y is equal to concentration A because it is the concentration after a period of time. Concentration A0 is the y-intercept and T is x. When we arrange we have concentration A is equal to negative Kt plus concentration A naught, equivalent to y is equal to mx plus b. We get the value of the slope as negative Kt, so we now know that the line goes down with time. And this is accurate because the reactant A is slowly consumed to produce the products after a period of time. Moreover, for the first order rate equation, when rearranged would be natural log concentration of A is equal to negative Kt plus natural log concentration of A naught, equivalent to y is equal to mx plus b. Recall that ln A naught over A is the same as ln A naught minus ln A. Then, we just had to do some transposing to get the final equation. The slope m is still negative Kt, so the line goes down with time. The y-intercept is ln A naught, and to solve for the actual initial concentration, we have to do the following. Again, recall that ln x is equal to 10 would be x is equal to e raised to 10, e being the Euler's number. Applying this, we have b is equal to ln A naught. When transposed, it would be A naught is equal to b raised to e. There we have the initial concentration. Last but not the least, the second order reaction will have the final structure of 1 over concentration of A equals Kt plus 1 over concentration of A naught, which is equivalent to y is equal to mx plus b. Finally, we have a line going upwards with a slope of Kt. We also have a y-intercept of 1 over the concentration of A naught, so we derive concentration of A naught by cross-multiplying.
To end this video, let's check whether or not you've learned something.